Okay, good evening. This is Professor David J. My topic for tonight will be a continuation of my long video format discussion AC machines, and I am now on lesson number 42. Okay, let's proceed. The subject matter for tonight will be AC machines, lesson number 42. The title of the topic will be Example Problem on Open Delta Connection. So this will now be an application of the concept of Open Delta Connection. Why are we always solving Open Delta Connection? In real life, Open Delta Connection is actually coming out because the problem with the so-called damaged transformer or transformer that must be repaired. So for us to have an electric power, utility companies try to connect their transformers and the so-called open delta connection. That's a real thing. The closed delta is actually just sometimes it's theoretical because in the actual field, we could not eliminate these actually defective transformers. Okay, let's try to bring out an example problem. Two transformers are connected open delta and deliver a load of 86.7 kVA at a power factor of 0.8. The delivered load of an open delta is given as 86.7 kVA. The power factor is 0.8. Since the power factor is 0.8, it's not 1. Obviously, the two transformers will deliver loads not equally, okay? Because for this to occur that the rating or the delivered load by each will be equal, it's actually at the power factor equal to 1, but the power factor is 0.8. So one of the transformers carry a higher load and the other transformer will carry a lesser load for a power factor of 0.8. Calculate. There are three requirements. The kVA load on each transformer. If the total power delivered is 86.7 kVA and they are connected open delta, what will be the kVA load of each winding? The problem is asking what will be the kVA here. Okay, and what will be the kVA here? Right? For a total load of 86.7 kVA, power factor is 0.8. Okay. Letter B, the kilowatt delivered, the true power delivered, or I just simply put it kilowatt delivered by each transformer, meaning the true power, kilowatt, and still the kilowatt over here. How much will be the kilowatt? Letter C, the available transformer kVA is apparent power. If a third unit of the same rating as one of the other two is added to form a closed delta. The problem is just asking if we try to complete this one, right? What will be the kVA of the third one? Okay? What will be the kVA of the third one? If we now try to complete this one as a closed delta, what will be the kVA of the third one? Okay, let's try to bring out the solution. Oh, this is an easy problem. It's just a matter of recalling the relationship of the, what you call this, apparent power relation of a closed delta and open delta. And actually we got the value here. The total apparent power for the open delta, the total apparent power delivered is 86.7 kVA. That is for open delta. And we got a relation that is the total apparent power for a closed delta equal to square root of 3 times the total apparent power of an open delta. This is where the 57.735% from our annotation. The relationship of the apparent power for a closed delta and open delta is 57.735. Or this is actually, if we try to compute for this, it should be the closed delta divided by square root of 3, or it will become 57.735% only. Okay, there are some values which are wasted. But if we are given the total apparent power delivered by the open delta by using this relationship here, this is a general concept. It will not change, right? So we know the open delta value, so we could compute for the closed delta value now by using this relationship here. This is a general equation, so this should be square root of 3 times 86.7. So if the connection will be a closed delta, okay, the total apparent power that could be delivered by it is actually 150 kVA. It's bigger than the 86.7 because it's a closed delta. There are 3 transformers now aiding each other. So if we try to compute for the kVA load of each transformer, taking now if it's closed delta, there are 3 now, right? And they could deliver 150. The problem is just asking the load for a closed delta if the total load is 150 kVA. If it's a closed delta, it's balanced already. Each of the 3 windings will carry 1/3. So the kVA transformer, if it's a closed delta now, will be 150 over 3, or it will be 50 kVA. Okay. For a closed delta, this is 50, 50, 50. So the total power that they could deliver is 150 kVA for a closed delta. But for an open delta, it's a different story. It's lesser. It's only 86.7. Okay, letter B. Letter B, the total true power delivered by each winding. Actually, I give you the concept on this one. It will be given by this equation here. In this equation. That is total true power is actually in kilowatts. This is in kilowatts. Will be the kVA per phase times cosine of 30 degrees minus theta. This is actually the power factor of the first winding. And the second one, the 30 degrees plus theta, is actually the power factor. I will place the subscript here 1, this is 2. 30 degrees minus theta is actually the angle difference between the voltage and current for line number 1, for winding number 1. And 30 degrees plus theta is actually the angle between the voltage and current for winding number 2. So this is minus, this plus. So these 2 values here are actually different. Because at different values of theta, they will deliver not equal loads. The only time that they will deliver equal loads is when theta is 0 degree. That is when the power factor is equal to 1. Right? But the given power factor is not 1, it is 0.8. So cosine of theta is equal to 0.8. Taking the arc cosine of both sides, the arc cosine of theta will be theta, and the arc cosine of 0.8. We could compute actually for theta. The arc cosine of 0.8 is 36.87 degrees. So computing the separately 30 degrees minus theta, this should be negative 6.87. 30 minus this. Second one is 30 plus theta. It will be bigger, this is plus. This is 66.87 degrees. So the first winding is operating at this power factor angle, and the second winding is operating at this power factor angle. So actually the total power delivered by each are actually different because the power factor is 1.8. So P1 now will be kVA per phase, cosine of 30 degrees minus theta, substituting values, heavy per phase is actually 50. 50 cosine of negative 6.37. The cosine of a negative angle is actually plus value. So if we try to calculate this one, it is 43.641 kilowatts. The second throw power, the second winding, it will deliver a lesser load because the power factor is different. This is kVA per phase, cosine of 30 degrees plus theta, 50 cosine 66.87 degrees. The cosine of this is small, right? It is smaller than the value of cosine of negative 6.87 because the cosine of negative 6.87 is actually almost equal to 1. It's almost 0. So the total power delivered by the second winding, if the connection is open delta, is only 13.64 kilowatts. Okay. So at the power factor of 0.8, this will carry 13.64, and the first one is 43.64. 43.64. The first one carry a higher load than the second one at the power factor of 0.8. So the total, the power delivered by H will be 43.64 for this one. Second one is 13.64. What's letter C? If we try to close the open delta, what will be the total apparent power that could be delivered? That's an easy one because we know that the voltage per phase is actually 50. So if we now try to close the open delta to a closed delta, the total apparent power that could be delivered by the three transformers will be 50 times 3, or simply 50 plus 50 plus 50, or that will be 150 kVA. It's greater than the 86.7 because it's a closed delta now. It's a complete delta. So this will carry 50, 50, 50. So if we close the original open delta, the total power that could be delivered will be 150 kVA. So you see the discrepancy from 150 to 86.7 at the power factor of 0.8. That's why sometimes it's needed that we close the open delta to a closed delta so we could maximize the total power, apparent power delivered. For the open delta connection, we just use that for a very short period of time. As soon as the third transformer is done, we will reconnect it, right? So it will now be a closed delta so that the total power delivered is 150 kVA instead of only delivering 86.7 kVA. Okay, that's it guys for tonight. Okay, this will be an example problem for the open delta connection. Okay, good evening from Los Angeles. Professor David J.